Hey everyone, so are you trying to understand how to work with maps in Java? If so, this video is for you. So in this video, I will go over a few topics, particularly answering the question of what are maps and their purpose, key value pairs, the Java map interface, and commonly used interfaces, handling duplicate keys, iterating over maps, creating and initializing maps, and some Java coding examples. As always, my video is timestamped, so feel free to click on this specific topic timestamp down in the description. So let's get right into it and let's talk tech with Tyler. So maps are an essential part of the Java collections framework, providing a powerful data structure that associates values with unique keys. So in this video, we'll explore the diverse applications and advantages of using maps in Java. So I have a table with a bunch of purposes of maps in programming as well as their description, and I'm going to go into detail for each of the purposes. So the first one is associating values with unique keys. So the primary purpose of maps is to establish a one-to-one mapping between unique keys and corresponding values. So this allows for efficient and direct access to values using their associated keys, making maps ideal for key value data representations. Another purpose is efficient data lookup. So maps offer highly efficient data lookup based on keys. With a constant time complexity for key-based access, maps enable quick retrieval of values, even for large data sets. And this makes them invaluable for tasks that involve frequent data lookup operations. Data organization and categorization is another purpose. Maps facilitate the organization and categorization of data based on their keys. So this feature allows for easy grouping and retrieval of related information, streamlining data management in various applications. Another purpose is implementing dictionaries and databases. So this application is crucial for building language processing tools, data storage systems, and more. Maps can efficiently count occurrences of elements in a dataset, and by using the elements as keys and the count or frequency as values, maps enables easy tracking and analysis of item frequency. Another purpose is indexing and search optimization. The index keys serve as references to the actual data, reducing time complexity of search operations. Another purpose is data representation and serialization. So maps offer a convenient way to represent complex data structures such as configurations of settings using key value pairs. They also aid in data serialization, allowing easy conversion between data formats. Another purpose is implementation of caching mechanisms. So maps are frequently employed in caching mechanisms to store frequently accessed data for quick retrieval. They enhance application performance by reducing the need to recompute or fetch data from external sources repeatedly. Another purpose is solving algorithmic problems. So maps play a crucial role in solving algorithmic problems such as graph-related tasks where nodes and edges are represented by keys and values. Their efficient data lookup and association properties make them valuable in algorithm design. And last but not least, another purpose is to represent real-world relationships. So maps are used to model real-world relationships where objects or entities are connected or related, and this allows developers to express complex associations in a straightforward manner. So as I discussed in the previous slide, the key and the value. So what is the key? So the key is a unique ID used to access specific value within a map, and the value is the data associated with a particular key. I have a coding snippet here of a map example, and in this coding snippet, we create a map called student map using the hash map class, which implements the map interface. The key type is integer, representing the student ID, and the value type is string, representing the student's name. We are going to do a Java code snippet example for working with maps, and we will be kind of creating something that deals with students. So first, we will do some import. We are going to import the hash map and map utilities. We just created a student records hash map. Now let's add some key value pairs to the map. So in line 6 and 7, we create a map called student map using the hash map class, which implements the map interface. The key type is integer, representing the student ID, and the value type is string, representing the student's name. After creating the map called student map, we then added key value pairs to the map using the put method. Each key value pair represents a student's ID and name. So for example, we have student map.put 1, John adds the key value pair with key 1 to value John to the map. So to retrieve values from the map, we use the get method, passing the key as the argument. So for instance, on line 17, student map.get1 retrieves the value associated with key 1, which in this case is John. The code snippet also demonstrates updating a value on lines 24 using the put method with an existing key. So in the example, student map.put 2, Oliver updates the value associated with key 2 from Tyler to Oliver. Furthermore, the code shows removing a key value pair from the map using the remove method. So here on line 27, student map.remove 4 removes the key value pair with the key 4 from the map. Finally, the map is iterated using a for each loop with the help of the entry set method. So each iteration retrieves the key and value using get key and get value method, respectively, and then just prints them. The Java Collections Framework is a set of interfaces and classes provided by Java to handle collections of objects. So examples include interfaces such as list, set, queue, and map. And that's what we're going to discuss a little bit more in detail is the map interface. So Java's map interface allows you to associate values with unique keys and retrieve those values based on the properties keys. There's 3 map implementations that I will discuss. It is the hash map, the tree map, and the linked hash map. I give a description, key characteristics, the order of elements, and the performance considerations in this table. So the hash map is an implementation of the map interface that provides fast and efficient data lookup. It uses a hash table to store key value pairs, allowing constant time complexity for most operations. So the hash map does not maintain any specific order for the keys, making it ideal for scenarios where the order of insertion or access is not critical. And the absence of ordering provides superior performance in terms of retrieval and insertion, especially for large data sets. However, as hash maps do not guarantee any specific iteration order, the iteration sequence may vary between different runs. The second map implementation is the tree map. And the tree map is a sorted implementation of the map interface that stores key value pairs in a red-black tree. It maintains keys in a sorted order, which makes it suitable for scenarios where keys need to be in a specific order, such as natural order. Tree maps provides efficient search and retrieval operations due to its logarithmic time complexity for these operations. So the tree map's sorted nature makes it useful in scenarios where data needs to be presented in a sorted manner, such as in alphabetical order or sorted ranks. However, the sorted structure leads to slightly slower insertion and deletion performance compared to the hash map. And a third map is the linked hash map. So the linked hash map is an implementation of the map interface that maintains a predictable iteration order based on insertion. It combines features of both hash map and the linked list, using a hash table for data storage and a linked list to maintain insertion order. So the linked hash map is ideal for scenarios where data access order matters. It guarantees predictable iteration order based on the order of insertion. So in this slide, I provide some example instantiation as well as some full Java code examples. This is helpful to look at, but I am going to actually go into some detailed examples right now. You might be wondering, how do we declare and create instances of maps using different implementations? So let's declare map, and let's do string, integer, and let's call it hash map. And let's create an instance, hash map equals new and let's add some key value pairs to the hash map. So how do we access a certain value? We can use the get method of the hash map. And what this will output is the value of 20. So moving on to the tree map, let us declare and let's create an instance. And let's add some key value pairs. And as you can see, we are going to use the same put method that we used for the hash map. Want to access a value, we will use the .get method with the key. So let's get 5. And this will output value 5. And let's do the linked hash map. So it's the same process. We will declare and do our key value variable types, which in this case is character and string. Let's create an instance. And let's add some key value pairs. And do you think we will use the same method? Yes, we will. So we'll use the put method and we'll type in a character and then the string. And to access the value, we will use the same method, .get. And I'm sure you can assume what the output would be. Banana. So in these three examples, we first declare a variable of type map with the desired key value types. Then we create an instance of the chosen map implementation by using the new keyword, followed by the corresponding constructor. After creating the map, we can add key value pairs using the put method and retrieve values using the get method. And remember, it's important to import the necessary classes. So as you can see on lines 1, 2, 3, 4, we have the java.util hash map, java.util tree map, java.util linked hash map, and java.util map. All four of these classes are necessary to use the map implementations. One of the fundamental aspects of managing data in Java involves handling duplicate keys within map implementations. So in this slide, we will delve into the behaviors associated with duplicate keys and explore how three commonly used map implementations, the hash map, tree map, and linked hash map, address this issue while ensuring data integrity and efficient retrieval. So in the case of the hash map, the presence of duplicate keys is not permitted. When attempting to insert a key value pair with a key that already exists in the map, the new value takes precedence, replacing the existing value associated with that key. So this feature enforces a unique mapping of keys to values, optimizing fast data retrieval based on keys. So for instance, if we add values for apple and banana, and then attempt to update the value for apple, the map will seamlessly update the value associated with apple while retaining the uniqueness of keys. Similarly to hash map, tree map also enforces the rule against duplicate keys. Upon attempting to add a key value pair with a pre-existing key, the new value supersedes the previous value linked with that key. However, tree map differentiates itself by managing a sorted order of keys. So this sorted nature positions tree maps as an apt choice for scenarios that want organized data. And comparable to our previous example, so if we input values for apple and banana and subsequently seek to update the value for apple, the map will efficiently update the value for apple while upholding its sorted structure. Unlike its counterparts, the linked hash map restricts the presence of duplicate keys. So similar to its counterparts, the linked hash map restricts the presence of duplicate keys. When trying to insert a key value pair with a duplicate key, the new value replaces the existing value associated with that key. Yet, linked hash map stands apart by guaranteeing a predictable iteration order based on insertion. So this predictability proves valuable in situations where maintaining a specific order of access is needed. In the context of our previous illustration, the map will effectively update the value linked to apple while also ensuring the consistent iteration order based on insertion. So what occurs in Java when duplicate keys are entered into the hash map, tree map, and linked hash map? So in this example, I'll demonstrate the behavior of each map implementation when a duplicate key is encountered. Basically, the existing value associated with the duplicate key is overwritten by the new value provided. Keep in mind this behavior may vary depending on the specific use case and the requirements of your application. So with the hash map example here on lines 10 through 16, created a hash map, created key 1, key 2, key 3. Then you could see I created key 2 again with a new value. So what do you think is going to print out when I access the value key 2? It'll be 40. It'll be 40 because the value has overwritten the 20. Moving on to the tree map example, we have 4 key value pairs in the tree map. And as you can see, key 5 has 2 values. So again, what do you think will be output? Value 6. And similarly, with the linked hash map, we have 4 key value pairs with B repeated. So the output will be blueberry. So basically, the existing value associated with duplicate keys is overwritten by the new value provided. Now keep in mind the behavior may vary depending on the specific use case and the requirements of your application. Let's discuss different approaches to iterate over elements in a map, including using the key set, values, and entry set methods. So efficiently iterating over elements within a map is a common requirement in Java programming. So in this slide, we will explore 3 distinct approaches utilizing the 3 methods shown on this slide, each offering unique advantages and considerations for traversing through map elements. So the key set method provides a means to access the keys present in the map, allowing for a straightforward iteration process. This approach is particularly useful when the focus is solely on key manipulation without requiring the corresponding values. So by obtaining the key set, developers can efficiently iterate through keys using enhanced for loops or iterators, enabling seamless access to individual keys for data processing. What about the values method? So that method returns a collection comprising the values contained within the map. So this approach proves beneficial when the emphasis is placed on value-oriented operations without utilizing direct access to the associated keys. So by acquiring the values collection, programmers can iterate through the values using enhanced for loops or iterators, enabling efficient processing of the stored values for specific tasks. And the entry set method offers a comprehensive approach to iterate over both keys and their corresponding values simultaneously. So by acquiring the entry set, a collection of key value pairs or entries, developers can effortlessly traverse through the entire map while accessing both keys and values in a cohesive manner. And this approach is particularly advantageous when requiring synchronized access to both elements for intricate data manipulation. So that's all that I have. I hope that you have a better understanding of how to work with maps in Java after watching this video. I hope the coding snippet examples were helpful. And if you have any questions, comments, or any suggestions for a next video, just leave a comment down below. And I do sell one-page cheat sheets that have everything that I covered in this video all on one page. So if you would like to get that one-page cheat sheet, I do sell them for very cheap. You can find them on my website, tylerlcrawford.com. All right, well, I hope you enjoyed this tech talk, and I'll see you in the next one. Peace.